On a sphere, the angles of a triangle add up to more than 180 degrees. The excess is not a flaw. It is the curvature made visible. One formula captures it all. The total curvature of any closed surface is locked to its topology. A sphere gives 4 pi, a torus gives 0, and a surface of constant negative curvature bends space so that parallel lines diverge forever. Every one of these is the same idea. Let us see why. Imagine you are an ant living on the surface of a sphere. You can walk in any direction. You can measure how far you have walked. You can check the angle between two paths, but you cannot jump off the surface. You cannot see the three-dimensional space around you. So here is the question. What geometry can you discover using only measurements made on the surface itself? Distances along the surface, angles between curves, areas of regions. This is intrinsic geometry. It is the geometry an inhabitant of the surface can detect without ever leaving it. And everything intrinsic is encoded in a single object called the first fundamental form. A smooth surface is the image of a map R from a flat patch in the UV plane into three-dimensional space. At every point, the partial derivatives r sub u and r sub v span the tangent plane. Now, to measure distances on the surface, take the dot product of tangent vectors with themselves. E equals r sub u dot r sub u, F equals r sub u dot r sub v, G equals r sub v dot r sub v. These three numbers give you the first fundamental form. Arc length, angles, areas, everything intrinsic, flows from E, F, and G. Let us compute E, F, G for 4 surfaces and see what they reveal. The plane, the simplest surface, E equals 1, F equals 0, G equals 1. No surprises. Now the cylinder. Parameterize it as cosine u sine u v. Take the dot products, E equals 1, F equals 0, G equals 1. Wait, those are exactly the same numbers as the plane. A cylinder and a flat sheet have identical first fundamental forms. The ant cannot tell them apart. The sphere is different. E equals r squared cosine squared v, G equals r squared. This is not the same as the plane. No matter how you bend a flat sheet, you will never make it wrap a sphere without stretching. The torus is richer still. E depends on V, so the intrinsic geometry varies from the outer equator to the inner equator. 4 surfaces, 4 sets of E, F, G, and already a mystery. Why do the plane and the cylinder share the same intrinsic measurements? You already know the answer from experience. Roll a flat piece of paper into a tube. Nothing stretches. Nothing tears. The grid on the paper becomes the grid on the cylinder, perfectly preserved. Both surfaces satisfy ds squared equals du squared plus dv squared. They are locally isometric. Distances are identical. This is not a coincidence. Something deeper is at work here, something Gauss called his remarkable theorem. What does it mean for a line to be straight on a curved surface? A geodesic is a curve whose acceleration is entirely perpendicular to the surface. Its geodesic curvature is 0. It never turns left or right within the surface. It goes as straight as the surface allows. On the sphere, geodesics are exactly the great circles, the curves you get by slicing the sphere with a plane through its center. The equator is a geodesic. Every meridian is a geodesic, and every tilted great circle is a geodesic. This is why airplanes fly over the Aleutian Islands on the way from New York to Tokyo. The route looks curved on a flat map, but it really is the shortest path on the sphere. On the cylinder, the answer is equally elegant. Take a cylinder and unroll it into a flat strip. Geodesics on the flat strip are straight lines. When you roll the strip back into a cylinder, those straight lines become helices. Vertical lines become straight generators. Horizontal lines become circles, and every line at an angle becomes a spiral. The same trick works for the cone. Cut along a generator and lay it flat. A cone with a 30-degree semi-angle unrolls into a half-disk, a sector of angle P. Geodesics on the cone are straight chords of this sector, lifted back onto the surface. There is one more thing geodesics reveal. Start 2 geodesics side by side, pointing in the same direction. What happens next depends on the curvature. On a sphere, where Gaussian curvature is positive, geodesics that begin parallel bend toward each other and eventually meet. Think of 2 meridians starting at the equator. They converge at the poles. On a flat plane, k equals 0, and parallel lines stay parallel forever. Euclid got it right. On a saddle surface, where k is negative, parallel geodesics spread apart exponentially. This is geodesic deviation, the way nearby geodesics accelerate toward or away from each other. It is the surface-level analog of tidal forces in general relativity. At any point on a surface, imagine slicing it with a plane that contains the normal vector. The cross-section is a curve, and that curve has a curvature. Rotate the slicing plane, and the curvature changes. The maximum and minimum values are called the principal curvatures, kappa 1 and kappa 2. They capture the most and the least the surface bends at that point. The average of the two gives the mean curvature h, which governs minimal surfaces like soap films. But the product gives something deeper. The Gaussian curvature kk equals kappa 1 times kappa 2, and unlike h, k is intrinsic. An inhabitant of the surface can compute it without ever leaving. The sign of k tells you the shape of the surface. When k is positive, both principal curvatures bend the same way. The surface is locally bowl-shaped. A sphere has k equals 1 over r squared, positive everywhere. This is the elliptic case. When k equals 0, at least one curvature vanishes. The cylinder looks curved from outside, but intrinsically it is flat. This is the parabolic case, developable surfaces. When k is negative, the two curvatures have opposite signs. The surface bends up in one direction and down in the other, a saddle. This is the hyperbolic case. The torus is the perfect showcase for Gaussian curvature. On the outer equator, k is positive. The surface curves like a bowl. On the inner equator, k is negative. The surface curves like a saddle, and at the top and the bottom, k passes through 0. The formula is elegant. K of v equals cosine v divided by b times a plus b cosine v. Curvature changes sign as you walk around the tube, and something remarkable happens when you add up all the curvature. The positive and negative regions cancel exactly. The total is 0. We will see why in the Gauss-Bonnet Theorem. In 1827, Carl Friedrich Gauss proved something he himself called remarkable. Gaussian curvature k depends only on the coefficients e, f, g of the first fundamental form and their first and second derivatives. Nothing else. This means k is invariant under any bending that preserves distances, any local isometry. You can bend the surface all you want, but k will not change. That is why the cylinder and the plane have the same k. They share the same e, f, g, so they must share the same Gaussian curvature, 0. No computation needed. The theorem hands it to you. Here is where Theorema Egregium truly shines. This is the catenoid, the surface you get by rotating a catenary curve around an axis. Its Gaussian curvature at every point is negative. Now watch. There exists a continuous family of surfaces that smoothly deforms the catenoid into a completely different shape. The helicoid, a corkscrew-like ruled surface. They look nothing alike, yet every surface in this family is isometric to every other. Distances are perfectly preserved at every instant of the deformation. And because distances are preserved, Theorema Egregium guarantees that k at corresponding points is identical. The curvature does not budge. You have been using Theorema Egregium your whole life without knowing it. A flat pizza slice has Gaussian curvature 0. Theorema Egregium says this cannot change when you bend it, as long as you do not stretch it. So fold the slice across its width. Now kappa 1 is not 0, but k must still be 0. Since k equals kappa 1 times kappa 2 is forced to be 0. The slice cannot droop along its length. Folding creates rigidity in the perpendicular direction. This is not folklore. This is a theorem proven by Carl Friedrich Gauss in October 1827. Everything we have built leads here. Draw a triangle on a sphere using 3 great circle arcs. Each arc is a geodesic. This octant triangle has 3 right angles. Each one is pi over 2. The sum is 3 pi over 2. That is more than pi. The Gauss-Bonnet Theorem tells you exactly how much more. Alpha plus beta plus gamma equals pi plus the integral of k over the triangle. On a unit sphere, k equals 1, so the excess equals the area of the triangle. 3 right angles, excess pi over 2, area pi over 2. It all fits. On a flat plane, k equals 0, and the angles sum to exactly pi. Euclid was right, but only in flat space. Now for the global version. Take a closed surface with no boundary and integrate k over the entire thing. The total is locked to the topology. The integral of kdA equals 2pi times 2 minus 2g, where g is the genus, the number of handles. The sphere has genus 0, k equals 1 over r squared everywhere. Integrate it. You get 4pi, always. The torus has genus 1. The positive curvature on the outer equator and the negative curvature on the inner equator cancel exactly. Total 0. A genus 2 surface, 2 handles, gives negative 4 pi. More handles, more negative curvature. This is the deepest fact in the geometry of surfaces. The total Gaussian curvature does not depend on the shape. It depends on the topology. Bend the surface, stretch it, squeeze it. As long as you do not tear it or glue new handles, the integral of kdA stays exactly the same. In 1854, Bernhard Riemann stood before Gauss himself and generalized this entire theory to spaces of any dimension. 60 years later, Albert Einstein used Riemann's framework to describe gravity not as a force, but as the curvature of space-time itself. There is one more way curvature reveals itself, and it may be the most surprising of all. Parallel transport. Take a tangent vector on a surface and slide it along a curve, keeping it as parallel as the surface allows. The rule is simple. The covariant derivative along the curve is 0. No deliberate twisting. On a flat plane, this is trivial. The vector keeps its direction no matter where you move it. But on a sphere, something strange happens. Place a vector at a point on the equator pointing due north. Transport it east along the equator for 90 degrees of longitude. The vector still points north. Now turn and go north along the meridian, all the way to the pole. The vector rides along, staying parallel. Finally, come back south along the prime meridian to where you started. Look at the vector. It no longer points north. It points east. It has rotated by exactly 90 degrees. You never twisted it. You never rotated it. The curvature of the sphere did this all on its own. This is called holonomy. The rotation angle of a parallel transported vector around a closed loop equals the integral of k over the enclosed region. For our octant triangle, k is 1 and the area is pi over 2, so the holonomy is pi over 2, 90 degrees. Exactly what we saw. You have seen this in the real world. The Foucault pendulum swings in a fixed plane, but Earth rotates underneath it. Over 24 hours, the swing plane appears to precess by an angle 2 pi times sine of the latitude. That is parallel transport on the curved Earth, the geometry of the sphere made visible in the swing of a pendulum. Now let us ask, which surfaces have constant curvature? Start with k equals 0. These are the developable surfaces. Surfaces you can unroll flat without stretching or tearing. There are exactly 3 types: the plane, the cylinder, and the cone. Every surface with k equals 0 everywhere is locally a piece of one of these 3. You see them in sheet metal, rolled paper, and architectural cladding. They are cheap to manufacture because flat material bends into them freely. Now, k equals plus 1. The unit sphere has constant positive curvature at every single point. And in 1899, Liebman proved something striking. The sphere is the only complete embedded surface in 3-dimensional space with constant positive Gaussian curvature. There is nothing else. What about k equals -1? That is the pseudosphere. Take a tractrix, the curve a dragged weight follows, and revolve it around its asymptote. Its area is exactly 4 pi, the same as a unit sphere. But its cuspidal edge makes it geodesically incomplete. You run out of surface. In June 1997, the mathematician Dana Taimina at Cornell realized that you could crochet a hyperbolic plane by increasing stitches in a constant ratio. But the pseudosphere has a fatal limitation. In 1901, David Hilbert proved that there is no smooth, complete isometric embedding of the entire hyperbolic plane into ordinary 3-dimensional space. The pseudosphere realizes hyperbolic geometry only in a local patch. The full hyperbolic plane simply does not fit. A subtle caveat. C1 isometric immersions do exist by the Nash-Kuiper theorem, but they are infinitely crumpled and not physically meaningful. So how do we see the full hyperbolic plane? We use a model. The Poincaré disk represents the entire infinite hyperbolic plane inside a finite circle. Geodesics appear as circular arcs that meet the boundary at right angles or as straight diameters. Every flat map of Earth lies. The Mercator projection preserves angles. It is conformal, but it distorts areas enormously. Greenland covers about 2 million square kilometers. Africa covers over 30 million. Africa is more than 14 times larger. Yet on a Mercator map, they appear roughly the same size. Why must every flat map distort? Theorema Egregium. The sphere has k equals 1 over r squared. A flat sheet has k equals 0. These are different, and k is an isometric invariant. No distance-preserving flattening exists. And here is a connection to our earlier video. The Mercator formula is itself a conformal map, the same angle-preserving idea that drove holomorphic functions. Everything in this video has a four-dimensional sequel. In general relativity, objects in free fall, planets, photons, you, do not follow straight lines in space. They follow geodesics in spacetime. Gravity is not a force pulling you downward. It is the curvature of spacetime telling you how to move. The angle sum formula on a curved surface, alpha plus beta plus gamma equals pi plus the curvature integral, is the conceptual ancestor of Einstein's field equations. Curvature is everywhere. In architecture, domes work because positive curvature creates natural compression. Saddle-shaped roofs need tension cables precisely because K is negative. In biology, kale leaves, lettuce edges, and brain coral all grow into shapes that approximate constant negative curvature. Nature discovered hyperbolic geometry long before mathematicians did. In computer graphics, the angle defect at a mesh vertex gives discrete Gaussian curvature, the foundation of surface smoothing and shape analysis. We began with a question: what can you measure without leaving a surface? The answer was the first fundamental form, E, F, G. From there, a flat pizza slice taught us that Gaussian curvature is preserved under bending. Two surfaces that look nothing alike, the catenoid and the helicoid, turned out to be the same, because their curvature is identical point by point. A vector, transported with no twisting around a triangle on the sphere, came back rotated 90 degrees, purely from the curvature of the surface. And the Gauss-Bonnet Theorem tied it all together. 4pi for the sphere, 0 for the torus. The total curvature is a topological invariant. Curvature is geometry made visible. Gauss-Bonnet is geometry made topological. If this story resonated with you, the next chapter awaits: the topology of surfaces and the Euler characteristic. Thank you for watching. If you enjoyed this, subscribe and share it with someone who has ever wondered why pizza stays rigid when you fold it. References and citations are in the description below.